Welcome, this is Physics 2211, Lab 3 with Jackson Greencorn. The purpose of this lab is to simulate through code the mass of a black hole and the necessary escape velocity of a rocket ship, using knowledge of parallel and perpendicular forces of motion. The end results should consist of a mass and a rocket that successfully orbits a planet without crashing into either the moon or said planet. The experiment is simple. We're going to use GlowScript software to construct lines of trial and error code to discover what escape velocities could allow the rocket to sustain orbit and what lines of code give the total mass of the black hole instead of a list of the masses after each trial run. So here's the setup for the black hole going from left to right, up and down. You'll see that the final line given is print the average is sum of the values divided by the length of the values, basically giving us a weighted average. For the setup of the rocket, you can see going from the top to bottom, setting up the vectors and position, then going into our calculations with our position and velocity update and force updates. Here are the outcomes. On the left, you have the black hole. We have the planet orbiting the black hole, and we have the average of the black hole given to us by 8.90031 times 10 to the 33rd kilograms, which makes sense. Black holes are super dense and very heavy. And on the right, you have a rocket that we guessed the correct escape velocities for it to sustain orbit but also not crash. The equations we use are simple. Net force in its parallel and perpendicular state, so F net is equal to F perpendicular plus F net parallel. The perpendicular net force itself has its own equation as mv squared over r. And then the velocity update formula, which we've seen before, and as well as the position update formula. And here, since we're in deep space, we use the universal gravitational force, Fg equals the gravitational constant, mass 1, mass 2, all divided by the radius squared. So what does this mean? And basically what I want to say is that the net force shows the instantaneous push or pull on an object, causing its motion to change. Its parallel component changes the speed, and its perpendicular component changes the direction. The change in momentum shows how the object's motion changes over time, while the rate of change of momentum equals the net force. Momentum change focuses on the before and after, and force focuses on the current cause. You can see force through instant acceleration and momentum change by comparing motion before and after a push or collision. So what if this imaginary system has a black hole, a star, a planet, and a moon? If I want to predict this, what would I include? Well, first off, I would include all of these. I would need their masses, their relative positions, their starting velocities, as well as everything that we had within the black hole coding and the rocket ship coding. I'd also need to know any relativistic facts about them. So concluding ideas, these forces are everywhere around us. We live on a planet that circles a sun inside of a solar system that gets affected by these forces every single day. Thank you.